Hello everyone, welcome to another session in the machine learning series. We'll continue our discussion on similarity measures. Right, so previously we discussed about cosine similarity. Right, cosine similarity could be applied to any sort of vector. So it could be a one-dimensional vector as we are seeing in the current image, or it could be two-dimensional as well. So only for say for understanding purpose, we are considering one-dimensional vectors and proceeding. So this is what cosine similarity is, right? So you have d1 and d2 as your vectors. The formula for cosine similarity of d1 and d2 is basically this, right? So we look at other measures now. This one is called as Euclidean distance. So I'm sure Euclidean distance is something which you have definitely come across right at the very beginning. Say it could be even in your school as well. So this is nothing but a distance formula, right? x2 minus x1 plus y2 minus y1 the whole square root of that. So this is what is Euclidean. Manhattan is sort of your absolute value distances, right? x1 minus y1, x2 minus y2, right? So this is what I think these three are the common ones. You have Euclidean, Manhattan. So you have Euclidean, you have Manhattan, then you have cosine similarity as well, right? So now that you have actually known the few distance measures, we'll actually look at how clustering actually works. All right. So what you see in the next this thing is what you see over here is nothing but this is your objective function for clustering, right? So this is your objective function for clustering. This is there, but what we'll actually see is clustering could easily happen in a three-dimensional case, could happen in a two-dimensional case, right? So what we'll basically discuss is say considering from a two-dimensional point of view, right? Mainly because it's easier to visualize how clustering is happening. Right, so say consider you're given a bunch of points, right? You calculate distance between them. Just because you calculate distance between them, you can't just randomly group them, right? So there should be a set of there should be a sort of a rule, or there should be a sort of an algorithm which would help, right? So what we'll discuss now is we'll basically discuss how clustering algorithm works in say a two-dimensional use case. Obviously, similar this thing can also be three-dimensional use case as well, but just for ease of understanding, we'll basically discuss a two-dimensional use case of the clustering algorithm. So right, so the first step would obviously be deciding the number of clusters. Say we'll definitely discuss on how do you decide a number of clusters, but for now, say you basically have three clusters, right? You basically have decided on three clusters, right? So this is how the two-dimensional use case is. You basically have a line, right? So you basically have a line where P1, P2, P3. So these are your points, correct? So P1, P2, P3, P4. These are your points. So C1 is your first cluster center. C2 is your second cluster center, and C3 is your third cluster center. Okay. So for each cluster center, you have your C1, C2, and C3. Then you have points. So here the first step is one, you randomly assign your cluster centers, and so that would be the first step. Randomly assigning your cluster centers. Okay, that's the first step. So what do you do next? So now you've got your cluster centers, right? So what do you do next? So the next step is basically just to give it a high level overview. What does the algorithm do is say basically for each point, right? For each point, you basically calculate the distance between the point and the cluster centers. Say distance between point P1 and C1, right? You call it as D1, say. Then distance between point P1 and cluster center C2 is D2. Distance between point C1 and cluster center C3 is D3. Now distance. Now this is where your distance measure. Comes into the picture, right? Now basically through these distance measures is what you are measuring. Okay, so you're measuring say distance between point C1 and cluster center C3. The D3, whatever D3 you see over there, right? That is where your cosine or Manhattan or Euclidean distance, all of those measures come into the picture. Okay, so this is the first step, right? So you basically calculate distance between point C1, cluster C1, D2, and D3. Now you have calculated all your cluster distances, right? The P1 and C1. So you basically calculate all your cluster distances. What is the next step is you basically assign the point to that particular cluster for which the distance is the least, right? That's obvious, right? So this algorithm is actually very, very straightforward. It's pretty straightforward, and it's actually very easy as well, right? So now you know p distance between p1 and c1 is d1, right? So among these three, among d1, among d2, among d3, the closest one is d1, right? So what you basically do is you basically assign point p1 to cluster to the first cluster, right? So it does not stop with assigning. So now your cluster center needs to be recalculated, right? Because you have additional clusters as well. You have additional points in the cluster as well. Sorry, you have additional points in the cluster as well. So your cluster center needs to be recalculated. Okay. Now this exact step is repeated for point P2. This exact step is repeated for point P3. This exact step is repeated point P4, P5, and so on. So basically for all the points, this literally the exact same step, distance between that particular point and each of the cluster centers, and assign that point to the cluster center for which it is nearest. Right. So this is what now say suppose you have done this process for all the points. What is next? Right. So cluster is basically an iterative process. Clustering is basically an iterative process. So you do not say in the first iteration you're not done, right? Since say this is again very similar to all of your previous iterative process which you have looked at, right? It could be your gradient descent, or it could be a tree building, right? So all of this followed a very similar process. For all of these were iterative processes first, and it followed similar logics. Basically, what is that logic is you need to have a stoppage condition. So basically, when do you decide to stop? Right? When do you reach convergence, or when do you basically decide to stop? Right. So that is what for every iterative process, right, you definitely would have a convergence criteria or stoppage criteria. For particular clustering, what would happen is, say in the first iteration you would go through all of the points, right? That is what happens in the first iteration. The second iteration, again the same step repeats. So after the second iteration, basically what you do is you would basically check the difference between cluster center is calculated in the first iteration and cluster center calculated in the second iteration. So here, if the difference between your cluster centers is again it's depends on your use case. Say let us say the difference between your cluster center from two iterations is lesser than 0.005, right? The process would stop. Okay. If not, the again process goes into again an iterative loop. So this is what is k-means clustering, right? For the first iteration, you basically calculate distance between point and each cluster center, assign that point to the nearest cluster center. Similarly, do the same thing for remaining points as well. So this is in your first iteration. In the second iteration, again follow the same process, right? And for the further iterations as well. So, but after each iteration, you basically check for the difference between your current cluster center and the previous cluster center. So if the difference between these is lesser than 0.005, you basically stop. So this difference, the difference in distance, is what is called as convergence criteria. Okay. So generally it is seen that after 20 to 50 iterations, right, it is generally observed that k-means clustering converges. So after 20 to 50 iterations. So again, this is generally, but maybe depending on your data and on your use case, this number might vary, right? So this is what is k-means clustering for you. Okay, coming back to remember in the initial part of this k-means clustering discussion, k-means clustering algorithm discussion, we just discussed that you need to decide on the number of clusters in the beginning only, right? So the algorithm does not tell you the number of clusters. As in, this particular algorithm does not tell you the number of clusters. So even before you start the clustering process, you should basically decide on the number of clusters, correct? Now that is what there's a method for that. So that is what we look at currently. So what is that method? Is something which is called as elbow plots. We use something which is called as elbow plot to basically decide on the number of clusters. What basically elbow plot is actually fairly straightforward. It's basically a plot of number of clusters on your x-axis, 1, 2, and 3, and so on. And on your y-axis, you have something which is called as average within cluster sum of squares. Yeah, even though it's actually fairly even though it's actually fairly supposed to be big, but it is actually very straightforward. So this is nothing but average within cluster sum of squares, right? Within cluster, what is the sum of squares? So it's nothing but, say you have a cluster, correct? Every cluster would have its own centroid or center, whatever you call it. So average within cluster sum of squares is difference between every point in the cluster from the center and you average it out for all your clusters. Say if you have 10 clusters, the first thing which you would do is for each cluster calculate the difference between that particular cluster center and the distance between a cluster and the points, right? So that is what this is, right? So this is xi minus xi is basically points within those clusters, cj is centroid for that particular cluster, right? So it's average within cluster sum of squares, so it's you're squaring it, okay? Then you basically take an average of it. That is what this is. That is what average within cluster sum of squares is. So this average within cluster sum of squares basically ends up on your y-axis. Okay, so this average within cluster sum of squares basically ends up on your y-axis. This is basically your elbow plot. So this is where your average. This is where your average within cluster sum of squares ends up. And on your x-axis you have something. On your x-axis you have something which is called as number of clusters. Okay, so on your x-axis you have number of clusters, and on your y-axis you have average within cluster sum of squares. Now coming to this elbow plot, so you basically fix on the number of clusters. How is that? You basically see this plot, right? So as your cluster number of clusters increases, your WCSS sort of goes on decreasing. So you basically fix the number of clusters as a point where you see that elbow, right? Where you see that drop, right? This is where you see the drop. It's like the point after this. So this is where you see the drop, and usually this is 3 or 4 would be your ideal sort of number of clusters, right? So see, fundamentally the idea is you basically decide if you basically choose more number of clusters, right? It would be very hard to separate it out, right? Because you see the error WCSS is almost constant. So even if you make 5 clusters, 6 clusters, you're not seeing a sort of drop in your WCSS. You're getting a sort of constant WSS, right? Because then basically what that means is whatever clustering algorithm you're running, it is not of much help, right? You're not able to group similar objects in a similar cluster because whatever grouping is done is already completed. All right, so that is why. So that is sort of the logic behind this elbow plot. Again, that's what. So when you understand what is clustering, right, all of this would seem would seem straightforward. So this is, so you stop at 3, or maybe if there's a further drop in this particular graph, it's not, there's no further drop, but sort of if you see again further drop, as in again when you divide the number of, as you increase the number of clusters, your WCSS also reduces further. It reduces more, then maybe you could even increase the number of clusters. But for this particular graph, right, for this particular graph, 3 would be a good number, where your average number of where your WCSS is reducing. So yes, this is what is k-means clustering. Again, hierarchical clustering does have its own algorithm, which we will discuss in further sessions. But for now, thank you guys.